Friends, welcome to the online class. I am Dr. SSC Hiremat. In this video, you are going to study about the Maxwell's thermodynamic equations. These equations show the relation between, that is, temperature, pressure, volume and entropy, which are derived from the thermodynamic functions such as Gibbs free energy, Helmholtz free energy, enthalpy and that is internal energy. Thus we can define these are the equations. These are the equations which show the relation between temperature, pressure, volume and entropy, okay, which are derived from the definitions of thermodynamic functions such as Gibbs free energy, Helmholtz free energy, enthalpy and internal energy. In this way, the Maxwell thermodynamic equations are nothing but the equations which show the relation between the temperature, pressure, volume and entropy, and these equations are derived from the definitions of there is Gibbs free energy, and there is Helmholtz free energy, enthalpy and internal energy. Now, derivation of first relation, that is from first and second laws of thermodynamics. Okay. Here, from first law, that is statement is heat given to a system is equal to increase in internal energy plus work of expansion done. So this is equation 1. Okay. From second law of thermodynamics, what is that? ds entropy change is equal to heat given to a system Q divided by T. On rearranging this, we get T ds is equal to Q. Okay, suppose this is equation 2. These are the arithmetical statements of first law and second law. That is, from equation 1 and 2, we can equate them. This is Q equal to this is equal to Q, means T ds is equal to dE plus PdV. This can be rearranged in this way, that is dE equal to T ds minus PdV. Okay, this is equation 3. Now we can apply the condition at a constant volume and at a constant entropy. Okay, that is at constant volume, P, that is dV equal to 0. Then equation 4 becomes, equation 3 becomes dE equal to T into ds. Okay, dE equal to T into ds. The same can be rearranged in this way, that is dou E divided by dou S at constant V is equal to T. So this is equation 4. Now here we assume that volume was a constant. Now you differentiate this equation with respect to volume. Okay, by differentiation equation 4 with respect to V, we get, it is at constant S, we get, that is dou square by, that is dou square E divided by, this is with respect to V means dou V into dou S, that is equal to dou T divided by dou V at constant S. Suppose this is equation 5. Okay. Now similarly we can apply the condition, the same equation. Okay, at the constant S, then ds becomes 0, then equation 3 becomes, okay, and S is constant. This is dE equal to minus P dV. Okay, on rearranging the same equation, we are going to get dou E divided by dou V at constant S, is equal to minus P. Suppose this is equation 6. Okay, now we have kept the S constant. Okay, S constant. Now you differentiate this with respect to S. Okay, then this becomes, that is V constant. Then differentiating equation 6 with respect to S, at constant V, we get, that is d square E divided by dou S into dou V as it is. This is equal to, differentiate this also with respect to S, that is minus dou P divided by dou S, and this is at a constant value. Suppose this is equation 7. Now equation 7 and 5 are similar, means left hand sides are same. Then from equation 7, that is 5 and 7, we get, that is T, that is dou T divided by dou V at constant temperature, constant S is equal to minus dou P divided by dou S at constant value. This is equation 8. Equation 8 gives the relation between temperature, volume, pressure and entropy, which was derived from the first law and second law of thermodynamics. From the definition of enthalpy. You can derive another interesting relation between the temperature, pressure, volume and entropy. That is second one. That is from the definition of enthalpy. Now, enthalpy H equal to E plus PV. Okay, then dH is equal to dE plus PdV plus VdP. Okay, this is then from this is equation 1. From the combined equation of first and second law, we get this is equal to TD. That is from combined equation of first and second law, that is T ds equal to dE plus P dV. Then from equation 1 and 2 we get from equation 1 and 2 we get what is that? dH is equal to T ds plus P dP. This is equation 3. Okay, now we want to derive this equation or find the differentiation at one at constant pressure and another at constant entropy. Now at constant pressure, constant P, we get that is dH is equal to T into ds. Okay, at a constant P, this dP becomes 0 and we get only this much. Okay, on rearranging this, we get that is dou H divided by dou S at constant P. That constant P is equal to T. Now, let us differentiate this with respect to P at constant S. Differentiating with respect to S as given. Now with respect to P at constant S, what we get? That is d square H divided by dou P into dou S. That is nothing but dou T divided by dou P at constant S. D square H divided by dou P dou S equal to dou T divided by dou P. Suppose this is equation 4. One was at constant P and another one at constant S. At constant S, equation 3 becomes and S is kept constant, that is dH is equal to P into dP. Okay, now on rearranging we are going to get dou H divided by dou P. This is at constant S. This is equal to P. Okay, now differentiate with respect to, now here with P it is differentiated. Now let us differentiate with respect to S. at constant P. At constant P. Then we get d square H divided by dou S into dou P, that is equal to dou P divided by dou S at constant P. At constant P. Now suppose this is equation 5. Equation 5. From equation 4 and 5. From equation 4 and 5. 4 and 5. We get, that is left hand sides are same. That is d square H, that is dou square H dou P divided by dou S. Okay. Then right hand sides are same. That is dou P divided by dou P at a constant S is equal to dou P divided by dou S at constant pressure. Now this is equation 6. Equation 6 gives the relation between temperature, pressure, volume and entropy, which is derived from the definition of enthalpy. Definition of enthalpy we derived. Okay, we got this equation. Let us derive the third relation, that is from the definition of A, that is Helmholtz equation, that is Helmholtz free energy. Helmholtz free energy, A is defined as A equal to E minus Ts, E minus Ts. On differentiation of this, we get dA equal to dE minus Tds minus S dt, Tds minus S dt. Okay, so this is equation 1 and this is equation 2. Equation 2. Then we know from the combination of second law and the third law, from the combination of combined equation of, from the combined equation of first and second law, we have, that is T ds is equal to P, that is dE plus P dV. Okay, that is equation 3, P dV. Thus we can substitute this dE into this equation, that is T ds equal to dE and P dV. We can substitute this from equation 2 and 3. Let us take equation 2, that is dA is equal to dE, that is dE. Okay, dE, and T ds equal to minus dE minus P dV. Okay, dE is here and minus T ds is equal to, T ds means dE plus P dV minus dE minus PV minus S into dt. Now this dE and dE gets cancelled. We get dA is equal to minus P dV minus S dt. Suppose this is equation 4. Now we can apply the conditions at a constant volume and at a constant temperature. At constant temperature, that is delta T equal to 0. Then equation 4 becomes equation 4 becomes, that is dA is equal to, when temperature is constant, dt equal to 0, this term becomes 0, that is equal to minus P into dV, P into dV. On rearranging this, we get dou A divided by dou V, this is equal to minus P, which is a constant here at constant temperature, okay. dA, dou A divided by dou V at a constant temperature equal to minus P, that is minus P, that is equation 5. Okay, now differentiate the equation 5 with respect to V. Now T is kept constant, okay, it is differentiated with respect to V. Now you keep the V constant and differentiate with respect to T. Differentiating equation 5 with respect to T at constant V, then what happens? Dou square A, differentiating with respect to T means dou T, and dou V remains as it is. This is equal to minus, and differentiate with respect to T, that is minus dou P divided by dou T at constant value. Now in the while differentiating with respect to T, V is kept constant, therefore this is at a constant V. Suppose this is equation 6. One was a constant and varied. Now in this case, you keep the V constant and T is varied. Okay, this condition is applied. At constant V, that is dV equal to 0, then the equation what is that? Equation 4 becomes, that is dA equal to dV equal to 0 means this term becomes 0, only this term remains, that is minus S into dt. Okay, on rearranging this equation, we get dou A divided by dou T at constant V, okay, this is equal to minus S. Suppose this is equation 6. Now T is kept constant, okay, at a constant, that is at a constant V, then at a constant V, the equation 4 becomes this. Now differentiate this equation, that is equation 6. Differentiate equation 6 with respect to V at constant T. Then what happens? Here differentiated with respect to V and T is kept constant. Therefore dou A divided by dou V into dou T. Okay, this is dou square 2 times. Okay, this is equal to, we are differentiating this S, that is minus dou S. Okay, dou S with respect to V means dou P, and that at constant temperature. Suppose this is equation 7. Equation 7. Now, equation 7 and 5, that is equation 6, are similar. Okay, this is equation 6, this is equation 7, and this equation 8. This is equation 7. Okay, equation 6 and 8 are similar because the LHS sides are same. LHS sides are same and RHS sides are equal. Okay, then equating equations from equation 5, that is 6 and 8, from 6 and 8, from 6 and 8. Okay, in this LHS are same, that is minus dou P divided by dou T at a constant volume is equal to minus dou S divided by dou T at constant temperature. Okay, both are with the negative sign. Both are with the negative sign. Thus we can rearrange, that is dou P divided by dou T at a constant volume is equal to dou S divided by dou T at constant temperature. That is, we can write this, we can remove this negative sign from both sides. That is equation 9. Equation 9. Equation 9 gives the Maxwell's thermodynamic relation between P, T, S and V, which can derive from the Helmholtz free energy equation. Now, the derivation of fourth important relation from the definition of Gibbs free energy, that is from the definition of G, that is G is equal to H into Ts. Okay, H into Ts. This can be also written as H is E plus PV minus T into S. Suppose this is equation 1. Equation 1 means H is substituted by E plus PV. This, on differentiation, we get dG equal to dE plus PdV plus VdP minus TdS minus SdT minus SdT. Suppose this is equation 2. Equation 2. From the combination of first and second law, from the combination of combined equation of first and second law, from the combined equation of first and second law, we have, that is T ds equal to dE plus P dV. Okay, this is equation 3. By substituting the value of T ds in this equation, that is from equation 2 and 3, we get, that is dG is equal to dE plus PdV plus PdP minus TdS is equal to minus dE minus PdV, okay, plus that is minus S dt. Now dE gets cancelled, and this is PdV, okay, this is PdV minus S dt, okay, and this PdV gets cancelled. Thus we get dG equal to V dP minus S dt. Suppose this is an important equation, that is equation number 4. Now we can apply the conditions, that is at constant temperature and at constant pressure. Now at constant temperature, that is delta T is equal to 0, okay, then equation 4 becomes that is dG is equal to V dP. Means when delta dt equal to 0, this term disappears. On rearranging this equation, we are going to get, that is dG by dou P at constant temperature is equal to V. Okay. On a differentiation of this equation, suppose this is equation 5. On differentiation of equation 5, on differentiation of equation 5 with respect to P, with respect to V, okay, that is with respect to T at constant P, we get, that is dou square D divided by, we are differentiating with respect to T, that is dou T into dou P, that is equal to dou V divided by dou T at constant pressure. Okay, we are differentiating with respect to T at constant pressure. Now suppose this is equation 6. Okay, now next one condition, at constant temperature is over, at constant pressure, dP is equal to 0. At constant pressure, dP equal to 0. Then equation 4 becomes, dG equal to that is minus S dt. Okay, minus S dt. This is dP equal to 0. Then on rearranging this equation, we are going to get dG divided by dou T, that is differentiating with respect to T, okay, that is at constant P, that is you are going to get, that is minus S. Suppose this is equation 7. Okay, now on differentiation of this with respect to P, on differentiation equation 7 with respect to P at constant T, we get dou square G divided by, we want to differentiate with respect to P, that is dou P, and dou T remains as it is. Then we are going to get minus remains as it is. We are differentiating with respect to P, that is dou S divided by dou P, and at constant temperature. Suppose this is equation 8. Okay. Now from equation 8, 6 and 8, from equations 6 and 8, we get, that is left hand sides of 6 and 8 are same, then automatically right hand sides are also same. Then we get, that is dou 3 divided by dou T at constant pressure is equal to minus dou S divided by dou P at constant temperature. Suppose this is equation 9. Equation 9 gives the relation between, that is pressure, temperature, volume and entropy, which is derived from the definition of free energy G.